Hello everyone, welcome to one more video. In this video I'll talk a little bit about timers and how do they work in a microcontroller. The examples that I'm going to give here are always related to the MSP430 microcontroller series. That is the one that I use in my courses. But the concepts that I will explain applies to most timers that you find out there in any microcontroller. Timers are basically made of three different components. A selectable time reference, which is the clock that you use to count time. An n-bit counter, so it's a register that counts +1 every time there is a rising edge of the clock. And a comparator. The comparator is a combination of circuit that receives two values and will compare if those values are equal. If they are equal, the output will be 1. If they are not equal, the output will be 0. So the time reference, the clock, we use to imply rhythm to the n-bit counter. And the counter will output a signal that we'll call time register or timer register, which is a number that when we translate, we can translate to time using the time step of the clock, so the period of the clock. And the value that we're counting on the timer register, we always compare to a certain threshold, which is a number that will be within the range of the n-bit counter. And whenever the counting register, the timer register, is equal to the threshold, an output value of the comparator will be equal to 1. So if we plot this in a time diagram here, we can see the clock running, the period of the clock right here, so the frequency is given by the inverse of the period. Every time there is a rising edge of the clock, the counter will count +1, and this value will count up to the limit of the n-bit counter. If we have a threshold, here denoted by the letters TH, for example, the threshold 4, and then we want to compare the value 11. The value of the output of the comparator, that I'm going to call it here a value of equality or equal, it's going to be 1 whenever these two signals are equal. So whenever the counting register here is equal to the threshold. So during this time window and during this time window here. So this is an important signal to know exactly when we have reached the value that we want to count. So these three components form up a timer. The time reference is basically a selectable clock. So there are, in this microcontroller that I use, there are mainly two types of clock that we can choose from: a slow clock to count long periods of time and a fast clock to count short periods of time with a lot of precision. The counter itself, it's a counting register, so whenever there is a rising edge, it will count +1. So in a simple example like this, when we count from 0 to 7, there will be a form of a stairway every time there is a rising edge. So the size or the time of the step here is exactly the same size of the period of the clock, which is the inverse of the frequency. The total time that I count is 2 times 2 at the power of n times the period of the clock, which in this simple example here is 8 times the period of the clock. So we count since we count from 0 to 7, we have 8 clock cycles at total. If I use more bits to this counter, this stairway will stay more fine-grained. If I use a lot of bytes, this is all for only 4 bytes, but if I use 16 bytes, this stairway is so precise that I'm not going to draw a stairway anymore. I'm just going to draw a line, okay? And I'm going to count from 0 to 2 at the power of n minus 1. So since the clock uses this counter, since the timer uses a counter like this, this timer can have different modes of operation. I'm not gonna do a complete reading of all the modes of operation. I'm just gonna explain two modes of operation which are very important for us. A continuous mode of operation, which is interesting to measure time, and a mode of operation called up, which we will see later. We can adjust the time that we want to count. So in the continuous mode of operation, the timer will count from 0 up to its limit, to its upper limit, which is 2 to the power of n minus 1. So this is the ceiling of counting. That's why we have a total period of 2 to the power of n steps of counting. But in the up mode, I can actually program the ceiling to be anything between 0 and the maximum here. So this threshold, the total time that I'll count, will be the threshold plus 1 times the period of the clock. So this is very interesting to track time or to count up to a certain given amount of time. Let's see some examples here. With 16 bits, the maximum time that I can count is 2 at 16 over the frequency of the clock. Using two different clocks, for instance, if I use a slow clock of 32 kilohertz, this will give exactly 2 seconds of counting. But if I use a fast clock, I will have only 65 milliseconds of counting at total. This is very interesting because we see a clear compromise here. We have a step of a large step on the first case of 30 microseconds, more or less, and in the second case we have a small step, a step of 1 microsecond only. So this is a very tiny step, which gives me a more precise counting. So there is a clear compromise here between the step size that I want to count and the maximum time that I can count. So this can be actually corrected very easily in software. We'll see how to do that in a second. So a timer has different channels. What are the timer channels? So we have seen that a counter receives a time reference, which we call here a timer clock, and this counter will output a signal that we have called a timer register, which is the counting value of the timer. This value will be compared to a given threshold, but we can have more than one threshold for a certain counter. So a timer can have multiple comparators, and each comparator will define a timer channel. The first channel, the threshold number 0, is very special. It has a special meaning of the ceiling of the counting, because this equal sign here is the only one which is capable of clearing the counter. So whenever I reach the threshold 0, the counter rolls back to 0. So the threshold 0 has this special meaning of ceiling of counting. Also, each equal sign will generate an interrupt flag or a signal which will stay equals to 1 until the processor clears it. So this is an interesting feature that we will use to signalize to the processor that the timer has reached a given amount of time, has counted a given amount of time. This signal we call an interrupt flag. I'm gonna explain why does it has this name in a second. So the group of a threshold, a comparator, and an interrupt flag is called a channel of the timer. The interrupt flag is an interesting signal that has the name from the mail system. When the mailman delivers a letter, it will deposit the letter into a mailbox and will lift up a flag indicating that there is a correspondence, that there is a letter for you. Whenever you see that flag lifted, you can check for new mail and will get the mail. So whenever you check and you get the mail from the mailbox, you will then lower the mail flag so you can realize, so you can know when there is new letters afterwards. So in these electronic systems, the mailman is the peripheral, so in this case the timer, and the person that is taking the letter out is the processor, in this case the CPU. I'm sorry that some words are kept in Portuguese because these are some slides that I've used in my courses and I forgot to translate some of these words, alright? So the timer is the mailman and the user program is the person that is going to get the letters. So the information is not so important in the mail system, in this electronic mail system. The event is more important than the information because the event is related to something that happened in that peripheral. In the case of a timer, that the timer has reached a certain threshold. So the interrupt flag, returning to our temporal diagram, the interrupt flag will go to 1, will be set whenever this equal sign goes to 1 in this rising edge of the equal sign. But the processor is much faster than the timer, so it will clear the interrupt flag as soon as it has reached its value. So the processor responds to that interrupt flag as soon as possible. And then when we clear the flag, we are ready to receive another event. If we don't clear the flag, we will not perceive, we will not realize that another event has reached, because we need this transition from 0 to 1 to detect that the event has happened. So this is an interesting system of communicating a hardware event to the processor. In the MSP430 configuration register, there is one register specific to configure the clock time reference and the counter, and another configuration register for the channel of the timer. So for instance, if I want to configure a given timer, I need to select an input timer. So I will configure the timer source select as select, which is a bit field inside the timer A control, for instance. So I can select, for instance, a clock by setting these bits to 0, 1, or by setting, using this macro, TA source select a clock, for instance. I can set up the counting mode using MC up, and I can clear the counting using TA CLR. So this line here will configure the timer to run in up mode and using the A clock as a reference. I can, for instance, wait until the interrupt flag from this register, for instance, this flag over here, when it goes to 1, I need to wait until the timer has reached this event. So I will use a while with no content, so I will use a while with a condition and a semicolon here. So this while will block the execution until the condition here is false. So I invert the condition so that whenever this flag is 0, this condition will be true, and the execution block here, this while, will stay forever in this line until the flag goes to 1. So this is an interesting system to block the execution until the flag turns to 1. Right after this blocking mechanism, we have to clear the flag because the flag has been set by the peripheral and the processor needs to clear. So we do this right afterwards. But in the microcontroller, there are a limited number of timers. Now, in the case of the microcontroller that I use here, I have only 4 timers in the system. A timer A0 that has 5 channels, the timer A1 and A2 that both have 3 channels, and a timer B0 that has 7 channels at total. If we look at these timers, it's very limited number of timers, and sometimes we need more timers than that. If we look into details of a timer, I can actually use one of these timers to create what I call a virtual timer. If a timer has 3 channels, we could actually think about measuring up to 3 different time periods using these 3 different channels. So we could have like 3 times being measured by the same timer. But what if I want more? What if I want 10 time measurements using a timer? So the idea here is to use virtual timers. We write a software that will compute time using a variable. Like for instance, we can create a variable, an array of timers of type 32 bits, so we can have a 32-bit counter. And n here is the number of timer instances that I want to create. If I want to create a new instance from this table of timers, I can then, like for instance, make a call to a timer new function. This we're going to see how to create. And I want to initialize this timer to 300 milliseconds, for instance. And I can query that timer to see if the timer is actually running. So while the timer is running, we do something. If it has ended or if it has timed out, we have to run an error procedure. So this mechanism right here is the mechanism that I like to use whenever I have to access a bus in a satellite system, because I don't want the system to block forever if the peripheral that I'm trying to communicate doesn't respond. If we want to use a blocking mechanism, I can also do it with this formalism. I can use a while the timer is running, don't do anything. So I use a semicolon here at the end to block the execution until the timer finishes counting. So this is an interesting idea that I work with a lot in my projects. So now that we have understood how timers work, let's talk a little bit how to implement this system using interruptions. So I'm going to talk a little bit more about interruptions in the next video. I see you there.